Hello. Today we will be presenting our project Phototanks, standing for Photonic Targeting Acquisition and Identification Knowledge Systems. I am Dylan Perkowski, and the other members of our team are Joshua Walton, Skyler Burns, and Joshua Frazer. Beginning with Phototank's project description, our system will be demonstrated utilizing a pair of remote control tanks operated in the first-person perspective in order to best simulate its real-world counterpart. The exterior of the hull will be covered in an array of phototransistors represented in the image by all the yellow circles. These are used for detecting the laser light emitted from the opposing tank. The lasers used will operate within two modes, being low and high power. When low power light is detected, an identification signal is transmitted from tank A to be received by tank B to identify tank A as friendly or hostile. The high power light is used when the respective tank fires its cannon and is detected as a hit by the receiving tank, causing damage to its health bar. Atop of the turret are three wide-angle cameras in addition to the camera mounted on the barrel, these of which all provide 360-degree video coverage around the tank. Utilizing AI, these video feeds are continuously analyzed for the detection and recognition of potential targets that will be brought to the attention of Phototank's operator. The conception of Phototank stems from the idea of tank laser tag. Building, the direction our project followed was largely motivated when assessing the big picture. Looking at the statistics, the United States has remained as the world's leading arms exporter. Within the 5-year span of 2016 to 2020, the U.S. controlled a 37% market share in international arms exports. Over that 5-year period, 47% of all arms exports went to the Middle East, with the largest recipient being Saudi Arabia. Even with the highly selective processes the U.S. government and the Department of Defense takes as to who and what they make international arms deals with, there will always pose a risk that any U.S.-made military equipment that isn't in the active possession of the U.S. military could be used against us. This led us to ask two questions. The first being, what if the U.S. goes to war against a country that also utilizes our military equipment and technology? And the second being, how would we be able to differentiate between friendly vehicles and aircraft and hostile counterparts if the battlefield is composed of two sides utilizing the same equipment? Taking a look into history, over the course of Operation Desert Storm, 9 Abrams tanks were destroyed. 7 of these were caused by friendly fire. Similarly, 28 Bradley infantry fighting vehicles were damaged or destroyed. 20 of these instances were caused by friendly fire. Of the Army's 615 soldiers wounded or killed in action, 107 of these cases were linked to friendly fire, being broken down into 35 soldiers losing their lives and 72 wounded directly due to one friendly vehicle engaging with another. Keep in mind, this was all fighting an enemy who wasn't using US-made equipment. Nearly all the reported instances of friendly fire occurred at night or in low visibility conditions. After the closure of the war, in response to these analyses, the U.S. Army began developing the Battlefield Combat Identification System, which functions similarly to our team's identification system. However, the Army discontinued and abandoned the project in 2003 due to costs of $100,000 being quoted per installation. Today, the current target acquisition process is still rooted in methods developed over the world wars, being comprised of a series of progressive and interdependent actions. These involve crew members utilizing the unaided eye and the use of optics to scan predetermined sectors of observation. This process can be lengthy and also includes needed communication through the chain of command. Also, some target acquisition methods and situations require for a crew member or members to be dismounted from the vehicle and exposed. Additionally, soldiers can be presented with challenges that hinder the process of acquiring potential targets such as reduced visibility, camouflage, mirage effects, natural terrain, etc.
This slide and the following are about the parts we have identified necessary and what we need for them. To start, for the tank turrets, we need a pre-built chassis that has a acceptable load capacity and plenty amount of points for the hull, and the chassis chosen might be the smallest of the bunch in both length and width, but it comes with an area to place the PCB we will be using.
The servo motor selected to rotate the tank's turret was selected for its fantastic cost versus performance compared to others on the market. The area of most concern when selecting this part was the motor's ability to overcome the frictional forces needed to rotate the tank's turret. Having a stall torque of 19.3 kg/cm assured us that we should never run into a rotation problem for the turret. A micro servo motor was selected to fit inside the turret housing in order to control the elevation of the tank's barrel. While the motor selected is rather expensive compared to other micro servos on the market, the performance specification to highlight is its pulse cycle of 1 millisecond. This allows for the motor to move in very accurate steps, providing the possibility for very precise adjustments to the barrel's elevation. We selected the L635P5 laser diode for a handful of reasons, the simplest being its pairing with the phototransistor's high responsivity around 635 nanometer light. Further, we selected a 5 milliwatt laser diode to save from accidentally blowing out or destroying one of the phototransistors. Also, a 5 milliwatt laser was selected to prevent it from being a class 3R laser where eye and skin damage can occur more frequently if directed at the eye or left in contact with skin. Lastly, having a price just over $25, the laser diode is rather inexpensive. Our group selected a plano convex lens as our lens of choice for photo tanks due to their good ability of focusing and collimating a laser beam. The lens we selected, LA1039, has a focal length of 9 millimeters. This positions the lens at a distance away from the laser diode that provides for the beam shaping characteristics we desire and will inquire more about on the next slide. Here we will compare two of the lenses from the previous slide, simulating them in Zmax. Those two lenses being lens LA1024 and lens LA1039, the one our group selected. Both are being simulated in a 10-meter environment to test our requirement specification of minimal beam waste up to 10 meters. Comparatively, lens LA1024 has a focal length of 4 millimeters versus lens LA1039 focal length of 9 millimeters. In both simulations, the source was located a distance away equal to the focal length of the respective lens. Looking at their beam spot sizes at the stop after 10 meters, it can be noticed lens LA1024 has a considerably smaller spot size. This is due to the lens having a smaller focal length than LA1039. In fact, the smaller the focal length of the lens, the tighter the beam spot would be, and the better the laser's beam would remain collimated. In this sense, the most appropriate lens for phototanks would be one that would be infinitesimally close to the laser diode. However, looking at where along the axial axis the beams come to focus, it can be noticed that lens LA1039 comes to focus at around half a meter, compared to lens LA1024 coming to focus at around 1/4 of a meter. While the beam from lens LA1024 diverges less and stays closer to the focus as it propagates, our team felt that a beam of these characteristics wouldn't be optimal for phototanks. Considering the ranges at which phototanks is going to engage with targets, we felt that having the beam come to focus at a range of half a meter would be best suited for where we expect phototanks to come into engagements. Meanwhile, at range, having the beam diverge out may help it be more visible on the camera, as well as better the chances at illuminating the phototransistors.
For our design, we chose the Intel 8265NGW for the Jetson Nano and the Hi-Let Go HC05 for the MSP430.
The camera we selected for the barrel has high resolution, an acceptable field of view, and great frame rate options. Being the camera that is going to act as the first-person perspective camera for Phototank's operator, our team felt it necessary to select a higher quality camera. The cameras selected for the chassis have high resolutions and good frame rate options, acceptable field of views being wide-angle cameras, and are priced at a decent cost considering that we are going to have to purchase multiple of these cameras. Similarly to the barrel camera, these cameras are also compatible with our Jetson Nano AI kit.
For the camera setup, we chose one camera per side of the tank. This makes it easy to identify which direction threats are coming from, as well as keeping the distortion low.
Here are all the actions that are needed to be coded up to have a fully functional tank. Obvious actions would be anything to get the tank to function like an average tank. That is getting the left and right motor to be able to follow basic tread movement functions. So if I needed to turn the tank left, I would need the right motor to go forward and the left motor to go backward to resemble a near 0-degree turn, and vice versa on a right turn. The turret base and the turret barrel is another obvious functionality that needs to be incorporated. As mentioned previously, the Jetson Nano will be our processing unit for anything AI. Our initial plan is to start off with a model that can do object detection and somewhat process certain objects from all cameras to automatically center that object to the barrel camera. The reasoning for this is to confirm what is being seen. For instance, if we see another tank behind us, then the barrel will just autocorrect the turret in the barrel to that tank and process if it's a friendly or hostile. If friendly, it will not shoot. But if it's hostile, it will engage its weapon systems and fire. If we have extra time, we will try to work on an instance segmentation model to test our capabilities and improve on our simpler design. This would of course be a separate model from our original one. Now, I try to put images of what each type of image and or video processing element is. A lot of people tend to not understand that there are multiple ways to process videos through AI. One of the most common, like in our project, is object detection. Looking at the picture, you can see that it identifies each object it was trained for with a bounding box and has a name to specify what each object is. Now looking at image recognition, you can see that it is very closely related to object detection, except you don't have bounding boxes. It just shows the name of what the AI is seeing. I'm pretty sure you can already guess why we selected to go with object detection rather than image processing. Just in case you don't, we needed a classification model that would show us each entity aside from one another. That is why object detection was the better choice. Now with segmentation, there are three common types of segmentation. You got semantic segmentation, instance segmentation, and panoptic segmentation. As you can see from the images below, each give you an intuitive idea of what each one is. Semantic segmentation tends to process each type of object as one specific color. Sometimes this can get confusing depending on the object you are trying to identify, due to not having bounding edges to signify which individual objects separate from one another. As you can see, this is our starting list of classification data we want to train our model with. We would like to have multiple types of tanks, trucks, jets, and infantry. We plan to add more data as we better perfect our model. As of right now, this would be our baseline. As shown, there are multiple different types of neural networks, or as we like to call them, CNNs. The ones we considered was ResNet, MobileNet, TinyYellow, and Single Shot Detector. Now with ResNet, this CNN was developed with deep neural networks in mind. the expectation being a lesser amount of lost data even with more layers within it. Normally, normal being within our CNN, at some point there are too many layers, in which proper communication lacks, and in turn takes longer to run and become less accurate. This CNN avoids this issue by ensuring there are some residuary connections between these layers. Because of this, this ResNet performs very well in any kind of project, even ones with much more fine details. Although ResNet is great and accurate for extremely large projects, it is a slower CNN, as shown in the graph. Due to that, and us not needing an extremely large size, we decided against using ResNet for this project. The next CNN is MobileNet. This CNN was initially proposed for TensorFlow as a computer vision model. It was made by Google and designed to be used for mobile devices or embedded systems. They are supposed to be very accurate, only use a small amount of power, and have a small margin of latency. It considers the restricted resources and constraints. For our data, we will specifically be referring to MobileNet version 2. This version is even faster and more accurate than its predecessor, MobileNet version 1. The CNN is a separable convolution. Basically what this does is factor out the layers to ensure that the size and time to calculate is kept small. This is one of the things that MobileNet is known for. Doing so helps with overall latency and positively affects the accuracy. We felt this was the best image classification for this project, and paired with the single shot detector for object detection would make it a superior option. The next CNN is Tiny YOLO version 3. YOLO stands for You Only Look Once. It got the name because it only looks the image one time, which is considered an open source method. This CNN works a bit differently than other object detection. In lay terms, it breaks the image into a series of bounding boxes. Each contain a confidence score regarding each class to get the predictions. Although it is still less accurate than the SSD, this is a good object detection if used for smaller, fewer specific projects. Lastly, the single shot detector. It gets its name because it uses the CNN on the image one time, and from there it can make a feature map. Although YOLO alone runs faster than SSD is slightly more accurate. This, of course, is dependent on the overall size of the object we are working with. If the object is too small, the accuracy of the SSD goes down. Like YOLO, it does use bounding boxes, but uses that with the convolutional layers and aspect ratios. Also, it works well with image detection components, meaning we can use it with ResNet or MobileNet, as shown in the graph. Lastly, it has extremely good accuracy and speed in comparison to other object detection models. Not quite as fast as Tiny YOLO alone, but matched with MobileNet and the use of all convolutional layers, it is. Between the speed and accuracy, those are two large factors that helped us come to the decision to use SSD MobileNet version 2 model for our project. The MSP430 carries many of the important logic required for our system. It does many of the features that doesn't entail AI functionality. Some of the important features are tank movement, making sure it's getting proper ADC readings from the phototransistors, relaying certain triggers like when to set off certain sound segments, operating the transceivers like they should, and of course our hit point hold. All of these are essential elements within our design that will be processed through the MSP430.
On this slide, we can see the individual DC to DC conversion circuits that were designed to meet our power needs. On the top, we have the HC05 Bluetooth module. Next, we have the MSP430 FR6989 IZB pinout schematic. Below that, we have the multicolor LED ICs. We also have functions for the laser diode driver, motor drivers, and light detection circuit. Starting from this page, we will get into the specifics of our design circuit. We will start with the phototransistor circuitry, also known as the light detection circuit. This circuit's general design allows us to shine a laser at any of the phototransistors and detect the intensity of the laser by measuring the resulting voltage drop. When the phototransistor receives light from the laser, current is generated. This current is then pulled to ground by the resistors at the top of the design. The voltage drop that results from the additional current being generated is then fed into the MSP430 through an analog to digital enabled pin. This ADC reads the voltage and generates a related number. This number is then compared to a predefined range that we decided upon to determine the light intensity that is present in the phototransistor. Depending on the range that this generated number falls into, the MSP430 will generate a hit signal. As far as the circuit design goes, the phototransistors are connected in series in groups of 4. Each group of the 4 phototransistors represents a side of the tank and corresponds to a different channel of the analog to digital converter. By analyzing which channel the voltage drop resulted from, we can determine which side of the tank is being targeted.